All right. So I always quickly remind what we have done the week before. So the week before, last week, we introduced what is a general graph. Be careful, it's always a set of vertices on a set of edges. But I introduced also a function I, because if you have multiple edges, you need this additional information. And this I is from the set of edges to 2 copies of the set of vertices. It gives you the initial point or the origin and the target. Then we have seen the difference between an oriented, which is the same as a directed graph, or an unoriented or undirected graph. We have defined what is a loop, what means multiple edges. A simple graph is a graph with no multiple edges and no loop. And a finite graph, be careful, you need to have this set finite and this set finite, both. Then we define the degree of a vertex, and I denote it by deg(x). We have also defined the minimal degree of a graph and the maximal degree of a graph. And what means that a graph is k-regular, it means all degrees are equal to k. Then the notion of subgraph, and more interesting is the notion of induced subgraph, because just taking a subgraph of a graph is not always the most interesting object, but the notion of induced subgraph is more useful. We have also defined what means bipartite graph. Then we define walk, trails, and paths. So walk, you just walk on your graph. Trail, you are not supposed to go 2 times through the same edge. And path, you are not supposed to go 2 times to the same vertex. There is a small clash of notations in this definition. This is an example of a graph with 1 walk. And when I define the names on edges, I just did it through this example. But in fact, I could give the names completely arbitrarily, and still I can take this path or this walk through the graph. It means I would go first through this E2, then E4, then E6, E8, E11, no problem. But yeah, if you look at the notation in the notes, yeah, it's an accident that I use the numbering with the same. I mean, I just follow this walk. It would be a problem if I do this and come back. Of course, this is still a walk, but I would not give a new name to this edge. I would just say, again, I take E5. This is just a small clash of notation, but I guess it's understandable. The distance has been defined, distance between 2 vertices. Be careful for oriented graph. In general, the distance from x to y is not the same as the distance from y to x in general. Of course, it can happen that they are the same, but not always. And this distance can be infinity. If you cannot go from x to y, we just say that the distance is infinity. I define the eccentricity as take the distance, eccentricity of x, take the distance from x to any y and take the maximal number. And then with this eccentricity, we could define the diameter of a graph, the radius, and what means central vertex. And there is one of the 3 reports is about the relation between diameter and radius. And finally, we define the notion of connected graph. Connected graph, you don't look at orientation of edges. So it's for undirected graph. Strongly connected is a notion for directed graphs. If you have any question, you can interrupt me at any time. And the notes have been updated, which means the material of this week and probably next week is already on the website. Okay. 1.3 is about cycles. Of course, in this course, we have many definitions, but it's necessary to have a common language. If you want to discuss about a subject with somebody, you need to have the same language. If one calls this cycle and another one calls this loop, we have a problem. All right, what is a cycle? So a cycle, and it's quite simple. A cycle is a closed path, a closed non-trivial path. Non-trivial because I don't want to call a cycle just 1 point. So what it means, you're in the graph and you do something like this. but your initial point and your final point are the same, and it's a path which means I cannot go 2 times through the same edge. I cannot go 2 times through the same vertex except the initial one. Okay, this is the notion of a cycle, and if G has no cycle, which is possible, you can easily construct an example of a graph with no cycle. If G has, no cycle, we call it acyclic. It has no cycle. And there is one more definition related to this notion of cycles. Can you give me an example of a graph or a family of graph with no cycle? Do you have a name? Yeah, a tree. I haven't introduced tree, but we will see this later. But if you consider a tree like this, clearly you have no cycle. I will come back to this in a few chapters. Still related to cycle, the girth of a graph. And this is written just girth of G is equal to the length of the shortest cycle. And this length has a meaning at some places, the shortest cycle, because of course you can have different cycles, and the length of the shortest one is called the girth. By the way, what is the minimum number of edges you have in a cycle? Think about, wait a second. Why? Yes, a loop, except if for some reason you decide that this is not a cycle. And for some application, probably it's not a good cycle.
Did you define cycle to be not true?
Yeah, but this is not trivial. A trivial would be just a point, and you just stay at the same place. It's not a cycle. But here you still do something. And if you have multiple edges, it can be 2. But in general, you expect this number to be 3. But be careful, it's not always the case. There is, let me state already this, what is on one report. There is a relation between the notion of bipartite and the notion of cycle. And the proof is already on the website. For G undirected and finite, let's say it's finite. G bipartite is equivalent to no cycle of odd lengths. Bipartite, remember, it means you can divide the set of vertices into 2 subsets, and each edge is between these 2 subsets. I let you think about it, but the proof is on the website. It's a nice exercise. And if somebody wants really to work on this again, you are free to do it. Even if a report is on the website, it doesn't mean you cannot work on the subject. Of course, you are not supposed to just copy and paste. You are not learning anything. But if you want to understand by yourself with different words, different explanations, this is possible. There is one special name. So special cycle What is a Hamiltonian cycle? A cycle in G is called a Hamiltonian cycle. Of course, this is from the name of somebody. It's called a Hamiltonian cycle if it contains all vertices. So yeah, remember it's a path, so you are not supposed to go 2 times through the same edge and 2 times through the same vertex. But if it contains all vertices, it's called a Hamiltonian cycle. And in fact, there is an important problem related to this. This is called the traveling Selman problem. Suppose you have to visit a couple of points and you have to go to all of them. What is the best way you visit all of them? And in fact, you can even write a report on this if you study this question, if you can find an algorithm for finding such a path, this is good. So if you want to implement this with some codes or whatever, you are free to do it. So yeah, study what means this traveling Selman problem. It's related with Hamiltonian cycle because you want to visit all points in a graph without going several times through the same path. Can you do it? Can you always do it? And the second definition, it's not for a path, it's for a trail. Remember, a trail, you are allowed to go. A trail, you are allowed to go 2 times through the same vertex, but you are not supposed to go 2 times through the same edge. So a trail containing all vertices, no, all edges, sorry, all edges of G is called Eulerian tree. And again, this has applications. You want to visit a city and you want to go through all streets without doing 2 times the same, without visiting 2 times the same street. It's exactly this. So you are allowed to go through a crossroad several times, but you want to visit all streets. And if it is closed, because you want to come back to the same initial point, it's called Eulerian tour. This is just name. And again, you can wonder, if I give you a graph, can you find a Hamiltonian cycle? Can you find a Eulerian trail? Of course, it depends on the graph. For example, in the tree I mentioned before, you have probably no chance to get a Hamiltonian cycle and no chance to get a Eulerian trail. But for some graphs, you can find the Hamiltonian cycle or a Eulerian trail. And if you can find a Hamiltonian cycle, you call it a Hamiltonian graph. If you can find an Eulerian trail, you call it an Eulerian graph. It depends. If you want to start and end up at the same point, for the name, Eulerian graph, yeah, it's okay. Probably for what is called Eulerian graph is if you can find an Eulerian tour, starting and ending at the same point. Yeah, you're right. Let me state one result, but there are other results, but let me state one which give you a necessary and sufficient condition for this problem. And if somebody wants to study the proof, it's most welcome. Connected, of course, it has to be connected. If the graph is in two parts, you have no chance to do this. A connected, undirected, and finite graph is Eulerian, which means has Eulerian tour. If and only if it's a necessary and sufficient condition. If and only if the degree of x is even for any x in the graph. It's an interesting result because you just check the degree. However, it doesn't tell you what is a trail. It's not constructive. It tells you, oh, you have a chance to find it, or you are sure to find it, but it doesn't tell you how. So if somebody wants to study this problem, I'm sure you can find many things on internet. Just Google this and you find a lot of information. And in the notes, there is one more exercise. I'm not going to write it, but there is an exercise about the minimal degree of a graph, the maximal degree of a graph. You can have some relation between these notions. The girth, the smallest cyclic, closed cyclic path, the diameter of G and the radius of G. So if you want to study a little bit these properties, you can look at this exercise. It's theorem 126. And again, you can work on this. The proof is not too difficult. And when I say you can work on the proof, it doesn't mean you have to find it by yourself. Sometimes it's difficult. But you can look at a book containing the proof, study, write it with your own words, your own explanations, your own pictures, and then you can submit it as a report. Any question or remark?
You cannot define that yet.
Wait, yes.
Should it be non-trivial as well,
What should be non-trivial?
this theorem? Because otherwise, one point is.
Okay. I'm sorry, but this is not the most interesting graph. I don't know if. Can you say that? Okay. No, I don't. You have another question or remark?
Cannot define it.
Yes, this was defined last week. Okay. You know, in mathematics, sometimes we take a lot of care about the very trivial situation, and we have to check that all statements are correct, even in the trivial situation. Sometimes it's just annoying.
Can we avoid this by redefining Euler shape by the length? Then say at least one.
If you want. Again, if you want to study this graph your entire life, you can do it. Weighted graphs. This is a very short section, but I want to emphasize one thing. For now, a graph is a set of edges, a set of vertices, and this function I, which allows us to work even if we have multiple edges. But sometimes we are interested in something more complicated. I want to put a number on each edge. For example, this edge has a weight 1, this one has a weight 1.5, this one 2, and this one is 0.73. For some reason, I want to associate a number to each edge. It's also possible to add a number for these points. I can also say, oh, this has a weight 2, this one has a weight 3, this one has a weight 1.5, this one is pi, whatever. For some reason, for some application, it's sometimes useful. And the correct notion is weighted graph. And you could even go further. Instead of having just a number, you could associate a vector for some reason. If you want to associate a vector on each edge, you can do it. I do the simplest situation where this vector is just a number. But okay, you can do more complicated things. So definition, a weighted graph so if I want to write everything, I should write this. It is a set of vertices, a set of edges. This I, which sometimes I don't write, especially if the graph has no multiple edges, it's less important. But now with the omega. And this omega is going to be what is called the weight. This is a weighted graph. It has 4 ingredients. Is a graph together with 2 functions. Why 2? Because you have 1 function for the vertices and 1 function for the edges. So with 2 functions, so 1 W or omega, it depends, from the set of vertices to R, and omega E from the set of edges to R. And this is exactly what I have here. Let me take the picture. This is E. So W of E is a number, 1.5. And let's say, this is W edge, because it's an edge. This is X, and this is Y. So we have a W V of X, which is, let's say, 3, and W V of Y, which is 1.5. Of course, it's arbitrary. So weight associate to any vertex a number, and to any edge a number. And so what is this W? Is simply the collection of these 2 functions. So I simply encode in 1 function a collection of 2 functions. And again, if you want to do something more complicated, you could just write Rn or a color, if you want to put a color, and this will come later. If you want to color your graph with 3 colors or 4 colors, then you just associate 1 color among 4 or 5. So this is quite natural. There is nothing special, but it's good to have the correct name. It's called a weighted graph. But now you have a natural question. Before I define the length of, let's say, a walk or a path, just by adding the number of edges. Now you can do something else. Oh, I want to minimize, let's say, the sum of the weights on edges. And this is exactly what happens in application. So the definition is a weighted length for, let's say, a walk is given by the sum of all weights on edges of the walk. Which means that if you go from this X to this Y through this path you have a weighted walk or weighted length of 2.5, while if you go through this path, you have 273. And for in the application, it might be interesting to find the smallest weighted path. And the weighted length can be different from the what I call the length, because here for these two paths, the length would be 2, but the weighted lengths are different from 2. So this is the weighted length, and just be careful. The length can be different from the weighted in general. Again. In fact, the one I introduced before is the special case where all weights are 1. If you put 1, you get the same definition. So for some application, you might be interested in minimizing such quantities. And the same, if so, for some reason you have a weight on vertices, you might be interested in minimizing the sum of the weight on vertices. And if you have orientations, you can even define a different weight on different edges, or even for unoriented. Even for unoriented, you could have a situation with 3 different weights on 3 different edges, because they are not the same if you have multiple edges. Or you can have something different of this type. So it's quite flexible. All right. So keep in mind, we can add information on edges and on vertices by functions defined either on the set of vertices or function defined on the set of edges. And then you can encode any information. Any question or remark? Yes? No, I don't have a special notation. If you need this notion, you just give a notation. And I don't, no. Even for the length, I have not introduced a, it's quite natural. You can introduce L for length of a walk. This is quite natural. And if now you are dealing with weighted, maybe you can add this subscript. But no, I'm not sure that you can find a standard notation for this, because it's very rare. You have a question?
Like a practical use kind of.
Oh, okay. Let's come back to this salesman problem. You want to visit a couple of points, but you have to pay a price depending on the path you take. You have to pay for something, so you want to minimize the cost. So finding the weighted length, which is the minimum one, is interesting. So if you have different way to go through all these points, you might be interested in having the minimal weighted length, because this is the cheapest path, or cheapest, yeah, length.
A most straightforward answer would be like the length, weighted length is the actual geometrical length of this line.
We haven't defined the geometrical length.
Imagine.
No, please. Okay, he's PhD students working on this subject, so we should not allow him to ask too many questions. Otherwise, we will never finish. Sorry. Okay. And he's in the math department, so it's even worse. But yeah, depending on the application, now if the graph is inside Rn, or if it is inside R2, this is maybe the real geometric distance or Euclidean distance. You can imagine everything. Okay, let's move to the second chapter, which is called representations and structures. So far we gave many names, but if you want to write a program related to graph, you cannot draw pictures like I'm doing. You need to encode this in something that a computer can understand. So how to encode a graph into what is the simplest thing is a matrix. How can we do it? So what is this idea, or the idea of this section or this chapter is to encode the information about a graph. In a matrix. Matrix are quite convenient. You are not obliged to do it in a matrix, but they are quite convenient. So the section 2.1 is matrix representation. So let me give you a definition for one way to encode information about one graph in a matrix. The graph has to be finite, otherwise you have infinite matrices. So I assume that the graph is finite. Let the I be a finite graph. On the other hand, it can be oriented or not oriented. So you may have arrows or just edges. And I assume that V, it contains a finite number of vertex, and I just give a name to these vertices from 1 up to a certain capital N. The adjacency matrix. This is called, and it's denoted, this graph is capital G. Is G. It's an n by n matrix. So it's the number of vertices which matter with value in R or even something smaller. Is defined by so remember, I want to encode the entire information contained in a graph. So what is the entry AJK? Oh no, AJK. So this is entry. You probably know this notation. You have a matrix, AG, and AJK is an entry with a line, J is a column K. So what is the information? It is the number of edges in E with I of E is equal to xj xk. Okay, so let's think about it. What is the meaning? You have your graph, complicated graph. Oh no, let me do a simple example. Maybe it's more efficient. First, it's not completely finished, but let me work on an example. Example is a simple graph. It is this. So we have 3 vertices and 4 edges. Okay. So what is the matrix? It's going to be a 3 by 3 matrix because N, capital N is 3. And I need to give a name. So this is X1, X2, and X3. The loop is just the only missing information. So let's check. A11, the first entry of the matrix, I need to look at edges which have initial point and end point 1, 1. Do we have any? No. We have nothing starting and ending here. So the first entry is 0. Then between x1, 2 and x2, 1, how many edges we have? We have 2 indeed. Because starting at x1 and ending at x2, we have 2. Then what about x2, 2 is 0? x1, 3 or x3, 1? No one. Now between x2 and x3, we have 1. And now what about x3, 3? So indeed, but look, yeah, it's a number of E. Now there is a convention which I should write. In fact, it is 2, because here with the convention, that a loop gives 2 contributions. But this is you decided. This definition, I take this. For some reason, later we will also use a convention that it's only 1. So you have to know the convention. It's not universal. You have to check what you do with the loop. But check now if somebody gives you this matrix, you can reconstruct this graph. So it means this contains everything. And what about oriented one? Still, the definition is fine. If now I put an orientation, I let you do the exercise. You can consider the same structure, but now let's do this. You can still do it. However, what is the difference? Or maybe we can, no, let me change, because otherwise, oh no, it was fine. I can keep this one. Now, what is the difference between oriented and unoriented? For unoriented, you can just look at this in arbitrary way. For oriented, you have to keep this order. So it means the matrix here is going to be 0. We have 1, 1. We have still 0. We have 0, 0. And now be careful. What it's going to, this is x2, x3. It goes from x2 to x3. So it is the entry 2, 3, which is 1, and the entry 3, 2, which is 0. So this is 1, and this is 0. And for the loop, I still keep this convention of 2. Is it line, the second line columns? So yes, it's going. Oh, no, wait. Let's go. Oh, no, sorry. I missed the convention. I didn't. So it gives 2 contributions for undirected graph. Sorry, yes, sorry. Undirected graph. And 1 for directed one, for directed graph. You're right, it would be wrong. But again, if somebody tells you, this is my rule, and gives you this matrix, you can reconstruct the graph. And what we observe, the matrix, the first one is symmetric. You probably know what is a symmetric matrix, which means you have a mirror on the diagonal. So it's symmetric for unoriented. This is true for all unoriented graphs, because precisely you can exchange these 2 entries, but it's not symmetric in general for unoriented. And we have additional things. Look at, let me write it. Look at the sum over columns or sum over lines. What do we observe for directed? What is the sum AJ K when you sum over, let's say, K? This is correct. This is the degree of xj. Think about it. You start at xj and you look at all edges starting at xj. It gives you exactly the degree. And this is why a loop will give the contribution 2. Otherwise, you don't get the correct answer. And in fact, this is also equal to the sum over k of a kj, because it's symmetric.
For undirected.
For, oh, sorry. Yeah, undirected, sure. Oh, thank you. And this equality is because of the symmetry. It's symmetric. Now, what about oriented? For oriented, in fact, we can say a little bit more if we define what is the in degree and what is the out degree. I mentioned last week that we could define this, but let's do it. So let me define a new notion, which I haven't introduced last week, for oriented graph. For oriented. And for any x vertex, we define the in degree, big N of x, and you can guess the definition. It's the number of edges so that I of E is yx for any y. The one coming to, the edges coming to x. So this one would count as an in degree for this point. And of course, you have the deg out, or the out degree. Again, you count the number of edges so that I of E is x, y for any y. Don't tell me that it's not correct.
Some should be over J.
Now, if I want to define the degree at xj, I cannot sum over j. Look, matrix is symmetric. So if you sum over lines or if you sum over columns, you get the same thing. Okay, so we define, this is quite natural. So the in degree would be 1 and 1. Here, the out degree is also 1. Here, the out degree is 2. The in degree is 1. And here, the in degree, again, loops. You would have an in degree 2, because you have 1 and 1, and probably an out degree 1. Yes?
Directed graph, does that mean that every edge has to be directed?
Yes, it was already asked last week. Probably you can do it more generally with a graph with oriented and non-oriented edges, but at least at this level, either I consider orientation everywhere or nowhere. But for some applications, you could probably, yes, have part of the edges with an orientation, part of them without. Then you need to adapt the notations. Yeah, it's probably a little bit misleading, so be a little bit careful about this. But then what we have in this setting, it implies that the degree of x is the sum of the deg in plus the deg out. This is clear. And you have other relation. The deg out of x can be obtained by doing the sum the sum over k of a jk, and the deg of x can be obtained by xk, the sum over j of a jk. Hope there is no mistake.
I think I'm right. It should be the sum of j, because if you go k, then you get the row, you're adding up the row. That's exactly what we want.
Please check carefully. The matrix is symmetric.
Oh, okay, then.
You know, I'm encourage you to ask questions, but I don't encourage you to just speak. So when you ask questions, please think about it. We can ask wrong questions, but not stupid questions.
Is this the reason loop contribute for two?
Up to you to decide. I mean, the people have decided some convention. It's because it's useful. If you don't put two, indeed, you have some problems. These relations are not correct. But now I will change the convention because for one application, for the next statement, we change the convention. You know, you're free to choose any convention, but you have to say it. You shouldn't hide anything. We change the convention, and it will be clear in the statement. And by the way, I also define for this course, I'm changing this definition every semester. N is 1 to 3, no 0. For some courses, N contains 0. For this one, it doesn't contain 0. Otherwise, you will see the next statement is stupid. Again, this is a convention, so I give you my convention for this course. Proposition. It's a very nice statement. Let A, G, the adjacency matrix. Adjacency matrix of a finite graph. It can be oriented or not. With loops giving one contribution. It means I change the definition compared to the convention I did before, both for directed and undirected graph. Then for any R belonging to N, so any integer 1, 2, 3, 4, 5, one has. I look at the matrix, this matrix power R. What is matrix power R? You take the matrix and you multiply it by itself R times. And now you understand why I don't want to have 0. Because what is a matrix power 0? And now I look at the entry JK of this matrix. So it's a product of R matrices, and I look at the entry JK of this. Can you guess what it is? What is this quantity? Without reading the notes. Look, the initial matrix gave us the link, the number of edges between xj and xk. Now when we take a power, it gives us the number of different walks between from xj to xk, which is quite surprising. And so I encourage you, the proof is given in the notes. You know, you have a graph. Let me come back to the, okay. Let me come back to this one, which was given before. Without the loop, probably it's a little bit misleading. What?
Off length part.
Ah, yes, off length. Thank you. Yes. I was too excited by this statement of length R. Look, suppose you iterate this matrix. How many ways you have to go from this point x1 to x3? No, because you can do this. Of course, you can do this, that's true. But you can also turn around here many times and finally come here. I'm thinking about about walks precisely.
For a given R, it's only.
Yeah, of course, for given R, it depends. But on the other hand, for going from x1 to x1 itself, you have also, either you can do it with 2 steps or with 4 steps or with 6 steps and so on. On the other hand, from x3 to x1, you have no way to do it. Yes, it's always you. So you can check, take the matrix corresponding to this graph, take iteration, 1, 2, 3, and so on, and check that indeed it gives you the number of different solutions you have to go from x1 to x3 with a path of length, with a walk. It's a walk. So it's a walk, which means I can turn around several times. So I think it's a quite nice result. Just everything is encoded in a matrix and in powers of this matrix. Again, and it works with or without orientations. And the definition is very precise, but be careful, it works only if you give a contribution 1 for a loop. So I have to change slightly the definition in order to make this statement work. That's it. Okay, so these adjacency matrices are very useful because dealing with matrices is rather easy. It's in algebra, and it contains everything. Now, if somebody wants to write a report about other applications of adjacency matrices, I'm sure you can find in many books or on internet how we can use these to obtain some information. There is a second information I want, or different presentation I want to introduce, is what is called the incident matrix. So it's another matrix which encodes information. But now the definition is slightly different for oriented or unoriented. So let G be first undirected finite graph. Again, with D, it contains capital N vertices, and the set of edges is E1. To be careful, it can be a completely different number, EM. So we have N vertices on M edges. So the incident matrix now it's defined, it's called IG, so incident matrix IG. It's a matrix, it's not a square matrix, it's an N times M matrix over R. So it's not square in general, N times M, defined by now this IJK, so the entry JK of this matrix, or no, JM. So it's slightly more complicated. It's 0 if xj is not an endpoint of the edge EL. So if Z, because now, remember, it's a matrix NM, which means the first entry is related to a vertex. The second entry is related to an edge. So it's 0 if xj is not an endpoint of the edge EL. It is 1 if xj is an endpoint of EL. I will make an example. And it is 2 if EL is a loop at xj. So let's look at an example. Again, I do the same picture. Unoriented, we are in the unoriented x1, x2, x3, but now I need to give a name to edges, E1, E2, E3, E4. So it's going to be a matrix 3, 4. And I give you the answer. You can check. It's 1, 1, 0, 0, 1, 1, 1, 0, and 0, 0, 1, 2. I let you check that it's correct because you have here it corresponds to x1, x2, x3, while we have e1, e2, e3, e4. And indeed, x1 is the endpoint of e1 and of e2. This is this 2, 1. x2 is a endpoint of e1, e2, e3. That's why we have 3, 1. And x3 is an endpoint of E3 and 2 times E4 because it's a loop. It's a way to encode the same information. By the way, observe that the degree of xj here is given by the sum over L of ijl. I'll let you check this is correct. And it's a sum from 1 up to m. On the other hand, Evidu, you can check.
The indexes,
Where?
the JL to be LJ. Because if you don't, then you have to sum over.
Wait.
No, no.
No, I see. According to my notes, so please check.
Sorry, I messed up.
Then you have also to do the second exercise like Evidu. Please check that this is always 2. Vertically, it's always 2 because it's in fact the 2 endpoints of any edge. So vertically, it's always sum up to 2. Horizontally, it gives you the degree. Now for oriented graphs. For oriented graph, as I said, the definition is slightly different. So I need to change it. For oriented finite graph. Let me directly give you this matrix. I don't write the sentence. IJL is given by 0 if xj is not an endpoint of EL, the same, it is 1 if xj is the target of EL. I introduce the target, so it is the endpoint of an oriented edge. It is -1 if xj is the origin of EL, and it is, again, it's a convention 2 if EL is a loop at xj. Again, you can check if somebody gives you such a matrix and gives you the rule, then you can recompose the graph. This is completely arbitrary. I mean, these numbers are arbitrary. If you prefer to put other numbers, as long as you don't have a use like the theorem I gave before, you can put any number. But probably for some applications, these numbers are good. So exercise or one report is please look for an application. What can you do? And I'm sure you can find in the literature some application of what is called the incident matrix. I didn't do it, but you can find this. All right. There is a second thing called incident table, because what happens when you have big graphs? When you have big graphs, most probably you are going to have many zeros, except if you have a very dense graph with edges between many, many points. But otherwise, if it's a graph with at every point only a finite number of edges, probably you're going to have many zeros. So sometimes we want to avoid so many zeros. So we can define what is called the incident table. It's written in the notes. Incident table, which eliminate all these zeros. On the other hand, there are no more matrices. And matrices are quite convenient because you just define a matrix and fill it. Incident table, yeah, it's not a matrix, it's just a table with a the information is encoded differently. Now, do you have any question? So remember, the aim of this section is if you have to code something, you cannot just draw a picture because your computer will not understand it. You need to encode a graph in a matrix or in something which can be read by a computer. Now I cheated a little bit. Just a little. Because when I said, if you give me such a table or such a matrix, I can reconstruct the graph. This is essentially true, but not completely. Let's look. For example, so this is called isomorphism. Let me draw first a picture with 3 points. Okay. This is a very simple graph. You can encode it in matrix. But now let me look at this picture. They do not look the same, but they are the same. It's clear that they contain the same information, but the picture is not the same. But if you give me the matrix corresponding to this, I can draw both pictures, because the matrix will give me that there is an edge between these 2 points, there is an edge between these 2 points, there is an edge here. It doesn't tell me if I have to draw it like this or if I have to draw it like this. So we want, of course, this is simple, but if you have a complicated graph, sometimes it's difficult to know if 2 pictures represent the same graph. And this is this notion of isomorphism. Even if the pictures are different, do they contain the same information? So if you understand that these 2 graphs, by the way, whenever I do a crossing like this, it doesn't mean anything. It's just because we are doing planar pictures, so on this plane, but it doesn't mean there is any crossing, except if I put a dot. But sometimes you might see this, but it's complicated. It means there is no crossing, it's artificial. So the good notion for understanding this is the notion of isomorphism. So these, let me just write a sentence. These 2 graphs look different, or they look different but they contain the same information. I want to give one or two definitions related to this. So the next definition is about isomorphism. It's a little bit long, but we will see that it's not so complicated. So I need to consider two graphs. G, which is V, E, and I, and G prime. Of course, it's not a derivative. It's V prime, E prime, and I prime. Just a second graph. You can call these V1, E1, and I1, and B2, E2, I2, but I use prime. A map. For me, a map, be careful, a map is just a function. It's the same. These two words are the same. A function or a map is shorter. It contains only 3 letters, but it's the same. A map F from G to G prime. Keep this in mind. I want to have, this is a graph, this is G, this is G prime. And I want to define a function from one graph to another graph. Okay? This is what I want to define. F from G to G prime is isomorphism of graphs. In the word isomorphism, you have iso, which means similar. Similar, you should think about this as similar structure. Isomorphism means similar structure. Isomorphism, an isomorphism of graph is a function from G to G prime. So F is if F, in fact, is 2 functions, like for weights. Remember when I introduced weights, in fact, I had 2 functions, one function about vertices and one function on edges. So it's a collection of 2 functions with, of course, you can guess the first one is about vertices, the vertices from G to vertices of G prime. So F index V is from V to V prime, and Fe is from the set of edges to the set of edges. We have 2 functions, one concerning edges and the other one concerning vertices, but they have to satisfy something. And satisfy 2 things. These functions are bijective. This you probably know what it means. Bijective, it means it's injective and surjective, which means let's say 2 vertices are sent to 2 different vertices, 2 edges, different edges are sent to 2 different edges, and you reach everybody. So it's injective and surjective. But there is a second condition, which is slightly more difficult to understand, but still it's natural. For any E in E with so I take an edge and I just call its initial point X, its final point Y. One has I prime of Fe. What is it? Can you guess what I have to write here? I take this function, I apply it on edge. So I take an edge here, I apply this F, which send me on a new edge, let's say this one. And then I want to have to look at the 2 endpoints. Then it has to be Fv of X, Fv of Y. Please think about it. What does it mean? it's a compatibility between these two functions. If you take an edge and look at the image of this edge, then the two endpoints have to be equal to taking this function, apply it to the initial edge, taking this function, apply to the final edge. No, sorry, to the initial vertex and to the final vertex, which is quite natural. Otherwise, it means these two functions would simply mix the information. They would do something on edges, do something on vertices, but there would be no compatibility, which is, I mean, this, let's put in color. This E is sent to this one, for example. But of course, I want this guy to be sent to this one. And another color, I don't have that. And this one to this one. Otherwise, it would be a little bit stupid. And be careful, this definition is also valid for oriented. What is the difference? For oriented, you pay attention to the order. So xy wouldn't be equal to yx. And you just have to be, here I wrote it correctly. I paid attention to the order, which is not necessary for an oriented graph. But if I want to keep the orientation, so which means if now this edge is oriented, I have to keep this orientation. The endpoint is the red one, the blue one is the origin. So this is the notion of isomorphism of graph. It's a bijective map, so you go bijectively from here to here, both for edges and vertices, but in addition, you have this compatibility condition, right? And still in this definition, I will give an example. Oh, this is the isomorphism of graph. If now I still give this one, of course, is sent on this one, and you do the corresponding, the same thing for the corresponding edges, you have an isomorphism of graphs. If f from G to G prime is isomorphism of graph, is an isomorphism of graphs, we say that G and G prime are isomorphic. This is a correct notion. These two graphs are isomorphic. They contain exactly the same information, even if the picture is different. The picture is not relevant. And we write, there is a notation for two graphs which are isomorphic. It is this sign with a wavelet. It's not an equality, it's an equality with a wavelet. And again, this definition is fine both for oriented and unoriented way. And now I'll do just a small parenthesis. If you want to have something nicer than this long equality, you can write a commutative diagrams, and mathematicians like commutative diagrams. The same information, you can forget this, but is encoded. So what do I need to write? I take an edge and I send it to prime, oh no, sorry, to B times V. Now vertically E prime. E prime. So what it is, what I need to write. These horizontal arrows are I and I prime. Any edge I associate its initial point, its final point. Any edge here, I associate its initial point, its final. And now what do we have vertically? Here we have the function fe. any edge in this set is sent to the edge here. What is this vertically? It's 2 copies of V. I should write it like this. And it's not surprising that it's 2 copies because look here, we also have 2 copies of this function. One for the initial one and one for the final. And what is the way to encode this information is to write this, which means it's commutative. So it's a commutative diagram. What does it mean? Again, you are not obliged to remember this, except if you are 4th year or higher. It means you can take this path or take this path, and you should obtain the same thing. And indeed, look, the left-hand side is in fact this path. I first apply Fe, and then I take I prime. And the right-hand side is the other one. I first apply I, it's encoded here, so I get X and Y, and then I apply to X and Y these 2 copies of Fv, and I have an equality. So this saying that this diagram is commutative is exactly saying this. Oh, it's the same thing. All right? So this is the notion of isomorphism of graph, or 2 graphs are isomorphic. It's a correct notion for saying that the information encoded here or here is exactly the same. And by the way, remark, it's an exercise. I'll let you think about it. This wavelet is an equivalence relation. Now you have to know what means equivalence relation. If you don't know, you Google it. I'm not going to say it, but it means it's 3 conditions. An equivalence condition is 3 conditions. You can, G is equivalent to itself. If G is equivalent to G prime, then G prime is equivalent to G. And if G is equivalent to G prime, which is itself equivalent to G second prime, then G and G second prime are equivalent. This is the meaning of an equivalence relation. And it's easy to check. If you want to do it correctly, the 3rd condition is the most complicated because you would have 2 pictures like this and you need to compose them. I'll let you think about it. It's not difficult. But now, as I said, there is a rather complicated question. If you give me 2 graphs, which are not so simple, complicated questions. Given G and G prime, if you give me 2 graphs, are they isomorphic? I gave a picture in the notes of 2 graphs which are not trivially isomorphic. So if you look at the 2 pictures, it's not clear that they contain exactly the same information. And if you make things a little bit more complicated, it's really difficult. Why is it difficult? Because if you want to answer this question, you have to find a function f which does the job. So you have to imagine all possible f and check if these f do the job. So it's not easy. Okay, it's a hard problem even for a computer if the graph is complicated because you have to check all possibilities. But there is a way to, this is a general rule in mathematics, showing that something is not is always simpler than showing that something is. Because if you want to show that something is not, it's sufficient to prove it very locally, or at least it's a simple condition. And this is an idea of what I'm going to introduce now. If you have 2 complicated graphs, you don't want to find all possible f. So if you have an argument for saying, no, it's impossible that these two graphs are isomorphic, then that's the end of the game. If you have an argument to say, oh, they cannot, for example, suppose you have a complicated graph, and you have 5, so the degree of this point, x, which is 5. This is a very complicated graph. And suppose you have another complicated graph, G prime, but beg of any y is never 5 for any y. Suppose that there is no point with 5. Then that's it. You don't have to check all possible f. If you can say, oh, in this graph, I have a vertex of degree 5. In this one, I don't have. Then no matter what you, or how many function f you try to construct, you won't be able to construct an isomorphism. So if you can prove simply, oh, I have a degree 5, I have no degree 5, that's it. They are not isomorphic. You don't have to check anything. So as I said, showing that something is not, sometimes it's easy. So we want to have a list of criteria which says, oh, if these criteria are not satisfied, then there is no chance that you can have an isomorphism. So this is called a graph invariant. And you have, you can imagine many graph invariants. So definition. A graph invariant is a property which is preserved through isomorphism. It means if the first graph has this property, the second one, which is isomorphic, has to have the same property. So if you know that one graph invariant is not the same in the two pictures, these two graphs are not isomorphic. So then this is really the key point. Let me write it in red. If G and G prime, so two graphs, have a different graph invariant, then they cannot be isomorphic. So it's a very powerful notion, this graph invariance. It doesn't solve the problem, but at least it eliminates many possibilities. So let's list some graph invariants. And in fact, if you want to be very precise, you should show that, it's a definition, they are preserved through isomorphism. So you have to check that indeed the list I'm going to give are graph invariants. I'm not going to check this, but it's rather clear. Some graph invariant. For example, the order and the size. Do you remember? Let me introduce the. What is the order of a graph? No, the order is the number of vertices, and the size is the number of edges. So if two graphs do not have the same number of vertices or the same number of edges, for sure they cannot be isomorphic. No way. So these are graph invariants. Of course, they don't say so much, but still it's an information. It's an easy information. The set of degrees. What it is a collection of all degrees. So take your graph, look at how many vertices have degree 0, 1, 2, 3, and so on. Do this list. Do the same list for the second graph. If these number of vertices with 0 edge, 1 edge, 2 edges, and so on are not the same, then they cannot be similar. They cannot be isomorphic. So you look at the set of all degrees with multiplicity. So a graph like this, what you are going to get is the set 2, 2. First point has degree 2, second point has again degree 2. You list this, and if a graph, of course, if I do this one, they cannot be isomorphic because for this one, this would be 1 to 1. Or you can, it doesn't matter in which order. It doesn't matter in which order because you don't know how you are going to create this function f. So you don't know x1 is going to go to another one. So you just do the list of degrees. Now, this is the same as 1 to 1. As a set, it's the same thing.
Can you have repeated elements?
Why not? Again, maybe for something it's not possible. I mean, you cannot have 2 students who are exactly the same. So in the set of all students, I cannot have a repetition. But in the set of tables in this room, of course, we have 18 tables which are exactly the same. About the same. Okay. Set of degrees. Now, something more complicated. Set of lengths of different paths or walks, walks, trails, or paths. So you have to be a little bit careful with this because it can be complicated, but you can, again, do the list of all trails or all walks or all paths. It might be complicated. Probably with walk, it's impossible because with walk, you can just turn around. So you have so walks is probably not a good idea, but trails and paths, you can probably do it. And if 2 graphs do not have the same set of lengths, there is no way. So this is another one. Another, a few others which are easy. And I will finish with these 2 examples. The diameter, we defined it last week, the diameter of G, or the radius of G, or even the girths, which I have introduced today, which are related with cycles. If 2 graphs have not the same diameter, the same radius, or the same girth, you have no chance to find an isomorphism. Think about it. And the last one, slightly more complicated, the set of degrees of neighbors. So what does it mean? Let me write it. It's complicated, but
You're defining a new function.
oh, n, I introduced it last week, is a set of neighbors. N of x is a set of neighbors. So what it is? You have again a complicated graph. Let's pick x. Again, it's a local information, but you don't have to look at the entire graph to do this. Pick a x. Then you look at its neighbors. We have 4 neighbors. And I look at the degree of each neighbor. So I would have 1. This one has 2. This one, oh no, sorry. The degree, it's 2, 3, 3, and 4. This is for x. X has neighbors with these degrees. This is for, maybe I can just write a x just to remember. And then I do the same for this point. This is now y. I look y, let's say this is like this. So the set of neighbors of y is, this one has 1, 2, 3, 4. This one has only 1, and this one has only 1. Okay? This is for the point. Of course, it's a very complicated list, but still is something you can look very locally. You just need to look at neighbors. And if you do this long list and compare it with a similar list for the other graph, and if these two lists are not comparable, no chance. Yes. Why unordered? Because we don't know which order I mean, I don't know if this one has to be exchanged or not. So you can decide to, maybe for, if you are writing this on a code, maybe you are going to order this because it's going to be simpler. But maybe, yeah, if you want to compare two sets, it's probably easier just to write 114, 114, and 2334. It's probably simpler, but yeah. Okay, so again, the idea is checking if two graphs are isomorphic is very complicated because you have to check all possible functions, which is usually very hard. But if you have a list of things which have to be equal in order to have such an isomorphism, and if one of them is not the same in the two graphs, then that's fine. Still, even if you draw a long list and they're all equal, it doesn't mean that the two graphs are isomorphic. So, except if you have a list which contains everything, but this is usually hard. But yeah, again, showing that something is not is simpler than showing that something is. So take the best of what is called graph invariance. And probably we are going to see others in this course. Okay, that's all for today. Thank you. If you have any question, you can ask me either now or send me an email or next week or anytime. And please start thinking about reports. You can check. We have 3 nice examples, but you can do something simpler. Okay. Thank you. Yes, I'm going to stop recording. Thank you for the one not in this room. If you have any question, you can also send me an email.